Now let's consider elliptic and modular functions as we still continue to talk about special functions. Elliptic and modular functions. Okay, I think I need to get rid of this. That's a repetition right there. Okay, now talking about elliptic and modular functions. Elliptic and modular function theory developed from the study of arc lengths of ellipses and eventually became one of the central subjects in modern mathematics. So, of course, you know the idea of ellipse. I talked about ellipse under conic sections as we considered coordinate geometry. So the development follows the sequence. How elliptic and modular functions came about. So we have elliptic integrals. From there we got elliptic functions, and then theta functions, and then we have modular forms. So these topics connect calculus, complex analysis, number theory, algebraic geometry, mathematical physics, and cryptography. And historically, the inability to express certain integrals in elementary functions led mathematicians to develop entirely new classes of special functions. And that is why we're here talking about elliptic and modular functions. So let's start with how it all started from elliptic integrals. So talking about elliptic integrals, right? Uh, the motivation is the ellipse, right? Consider the ellipse x squared over a squared plus y squared over b squared equals 1. Using the parameterization that x equals a cos theta and y equals b sin theta. So if you fix all of that up, then we end up getting the arc length, which is integral of the square root of a squared sin squared theta plus b squared cos squared theta d theta like that. So that will mean we have x squared plus y squared like that. But then we change it in terms of cos and sine. Unlike the circle, this integral cannot generally be expressed using elementary functions. So this led to the theory of elliptic integrals. So general definition, an elliptic integral is an integral of the form integral r of x, comma, square root of p of x dx, where r is rational, p of x is a cubic or quartic polynomial. Examples, you have the integral of dx over square root of 1 minus x raised to the power 4, or integral dx over square root of x cubed plus x plus 1. So both of these are considered to be elliptic integrals. So rational, as you can see, and then it's in terms of x, right? And then you have square root of something like p of x. Here it's 1 minus x raised to the power 4. So it's a cubic or quartic. So this is quartic here and this is cubic down here. So, and then we have Legendre standard forms. Legendre showed that some elliptic integrals can be reduced to three standard forms. So we have the elliptic integral of the first kind, that is f of phi, comma k, which is equal to integral from 0 to phi of d theta over square root of 1 minus k squared sine squared theta. The parameter k is called the modulus. And then we have the complete elliptic integral of the first kind. So if we set phi to be pi over 2, then that gives us that k of k is equal to integral from 0 to pi over 2 d theta all over square root of 1 minus k squared sine squared theta. So this quantity appears throughout elliptic function theory. And then we move on to the elliptic integral of the second kind, which is e of phi comma k, that's integral from 0 to phi square root of 1 minus k squared sine squared theta d theta. So instead of having this as rational, we have it not rational like that. Then we have finally the elliptic integral of the third kind, that is pi, so to speak, of n semicolon phi comma k, and that is equal to integral from 0 to phi d theta over 1 minus n sine squared theta into square root of 1 minus k squared sine squared theta. And by way of example, if we evaluate k of 0, right? K of 0, just like maybe we have k of k. So now this k is 0 here. So k of 0 would mean we have d theta over square root of 1 minus, in fact, the theta, because that's all that we have in left. So k of 0 will be integral from 0 to pi over 2, 1 over 1 d theta, right? And that means you just have d theta. So, and at the end of the day, you're just going to have pi over 2 like that. And pi over 2 is simply 3.712 divided by 2, thereabout. And then k of 0.5. Okay, k of 0.59 is like 1.68575 And then we move on to the inversion of elliptic integrals. So recall that u is integral from 0 to x dt over square root of 1 minus t squared, and that the whole of that is arc sine of x. I mean, we came across that if you differentiate arc sine of x, you end up getting 1 over square root of 1 minus x squared. So inverting that would give, if u is arc sine of x, if you take sine of both sides, it means that x will be equal to sine u. So thus trigonometric functions arise as inverses of integrals, right? So, um, elliptic functions are obtained by inverting elliptic integrals. So, if you consider u to be integral from 0 to x of dt all over square root of 1 minus t squared into 1 minus k squared t squared, its inverse is defined by x equals Sn into u comma k. This is the first Jacobi elliptic function. So Sn into u comma k, not sine, just Sn here. So, and then we go ahead to talk about elliptic functions. A function f of z is elliptic if f of z is meromorphic. There exist two independent periods, omega 1, comma omega 2, such that f of z plus omega 1 is equal to f of z, and f of z plus omega 2 is also equal to f of z. Then the ratio omega 1 over omega 2 is not real, it's complex. you know. Then we have the comparison with trigonometric functions. The sine function satisfies that sine z plus 2 pi is sine z, therefore sine has one period. Elliptic functions possess two independent periods and are therefore doubly periodic. So elliptic functions are doubly periodic. So the periods generate a lattice where you have alpha, I think this is alpha equals m omega 1 plus n omega 2, such that m and n are integers. Every elliptic function repeats itself on this lattice. Then we go to talk about Jacobi elliptic functions. So the fundamental Jacobi elliptic functions are Sn u comma k, Cn u comma k, Dn u comma k, and they generalize the trigonometric functions. So talking about fundamental identities now, it is analogous to sine squared x plus cos squared x equals 1. Treating trigonometry, we saw this a lot, and this particular identity is very useful in many instances for resolving many trigonometric problems. So just like that, we have sine Sn squared u comma k plus cn squared u comma k is equal to 1. A second identity will be that k squared sine squared k squared Sn squared u comma k plus this n squared u comma k would also be 1 like that. Then we can have a special case when k is 0. So when k equals 0, the Jacobi functions reduce to ordinary trigonometric functions, like when we say sine u comma 0. So because k is 0 now, that's just sine u. Cn u comma 0, that will just be cos u because k is 0. Dn u comma 0, that is just going to be 1 like that. Then we can have, so if you take from SciPy to special, you import ellipj, you know. Um, so we have elliptic functions as part of the SciPy special module under SciPy, right? So if you take u to be 1.0, m to be 0.5, and then you want to get Sn, Cn, Dn, and phi, so from elliptic J of U and M like that. So you print each of this and you can do the identity check to see if Sn squared plus Cn squared will result to 1, and that's exactly what happens. So Sn is 0.80 blah blah, Cn is 0.59 all that, Dn is 0.82 all that. The identity check is that when you add Cn squared plus Sn squared as expected, you get 1.0 that way. Then we have the Weierstrass elliptic function. The Weierstrass function is one of the most important elliptic functions. It is defined by, I don't know what to call this symbol. So let me say special P of z, right? Equals 1 over z squared plus summation of omega over alpha take away 0 of 1 over z minus omega all squared minus 1 over omega squared. The subtraction term ensures conversion. So this ensures convergence rather. So this ensures that it keeps reducing towards a particular value. It keeps declining. And then we have the fundamental differential equation. The Weierstrass function satisfies that uh, special p prime of z all squared is equal to 4 special p of z raised by 3 minus g2 special p of z minus g3. So this equation then connects elliptic functions with elliptic curves. So talking about the Weierstrass elliptic function. So talking about elliptic curves now, an elliptic curve can be written as y squared equals 4x cubed minus g2 of x minus g3. So every complex elliptic curve corresponds to a lattice in the complex plane. And then we have other kinds of, we have theta functions, which we referred to the other time. Theta functions are special infinite series associated with lattices. They provide explicit formulas for elliptic functions and modular forms. So first we have the Jacobi theta function. The classical theta function is theta of z comma tau is equal to summation from minus infinity to infinity of e raised power pi I n squared tau e raised power 2 pi I n z, where the imaginary value of part of tau is greater than 0. So, and then we also have the parameter q. So the parameter q, if you define q to be e raised by pi I tau, did you see that here? Okay, we have q to be pi I tau, right? Since the imaginary part of tau is greater than 0, then we can have that. So the imaginary part here is greater than 0. So we can have that the absolute value of q is less than 1. Therefore, the theta series converges rapidly. Okay. Then an example of this would be that if you have tau to be I, we obtain that q, because tau is I now, you know, tau is I, so it means we have I squared up there. So it means that q will be e raised by minus pi because I squared is minus 1. So q is minus pi. And then the series becomes theta of 0 comma I, and that is summation from minus infinity to infinity e raised by minus pi n squared. That's following the theta expression we have here. So if you fix all of that up, right, we get summation from n equals infinity to infinity of e raised to minus pi n squared. So approximating by the first few terms gives theta of 0 comma I, that's approximately 1. So it's just like expanding this whole thing up. So you have 1 plus 2 e raised by minus pi plus 2 e raised by minus 4 pi, and so on and so forth. Now, we then have, okay, I mean, we can demonstrate that here. We have to import numpers np. Tau is 1j, that's complex. Theta is 0. So for n in range minus 30 to 31, we can have theta plus or minus exponent pi n squared tau, like that. So if we print the real part of theta, we get this like that. 1.08643481121133082. Then we also have the important theta identity. The Jacobi theta function satisfies theta sub 3 super 4, which is equal to theta sub 2 super 4 plus theta sub 4 super 4. This identity resembles the Pythagorean theorem and plays a central role in modular form theory. Okay, that's an important theta identity. Then we have modular transformations. Consider the upper half. This special H equals is the collection of all tau belonging to complex numbers such that the imaginary part of tau is greater than 0. So we have a modular transformation which has the form tau such that a tau plus b over c tau plus d, where a, b, c, d are integers and ad minus bc is equal to 1. So we have a modular transformation in that sense. And then we also have a modular group. So for a modular group, it's going algebraic now. The matrix is A, B, C, D with AD minus BC equals 1. Form the modular group SL2, comma Z, that's special Z, that's integer now. For example, if you take pi to be I and apply tau, tau goes to minus 1 over tau. Okay. Then, and that gives that 1 minus 1 over I is equal to I. Therefore, I is a fixed point of this modular transformation. So I is a fixed point of this modular transformation. And then we have some other modular forms. So a modular form is a highly symmetric holomorphic function on the upper half plane. By definition, a modular form of weight k satisfies that f of a tau plus b over c tau plus d is equal to c tau plus d raised by k f of tau for all matrices in SL2, z. In addition, f must be holomorphic. So then we have Q expansions. If you define Q to be 2 pi I tau, most modular forms can be expanded as f of tau to be, which is equal to summation from n equals 0 to infinity of a sub n q raised by n. This is called the Fourier expansion or Q expansion. And then we have the Eisenstein series. The Eisenstein series of weight 4 is g sub 4 of tau equals 1 plus 240 summation from n equals 1 to infinity sigma sub 3 of n q raised by n, where sigma sub 3 of n is summation d slash n d raised by 3, like that. Talks about the Eisenstein series. And for example, if we have to compute sigma sub 3 of 4, the divisors of 4, so think about the divisors of 4, those are 1, 2, 4. Therefore, sigma sub 3 of 4 will be 1 raised by 3, 2 raised by 3, 4 raised by 3. That's it. I think that's a beautiful thing. Talking about the Eisenstein series like that. So that we then have q sub 3 of 4 to be 1 plus 8 plus 64, which is 73. I think I'm interested in this series. I'm interested in that so much. Okay, so if we do that here, so you define sigma so 3 of n, total is 0, that's initialization. So for d in range 1 to n plus 1. So if the modulo division of d is equal to 0, then the total will be plus equals d raised by 3. Then return total. So you print sigma sub 3 of 4. That's 73, just like what we have here. So this is the code form of getting this same thing. And this condition here is what determines that you have only things that divide 1, 2, and 4, like that. And that's what line 5 is about. So we have that. Then we have the delta function. The most famous Cusp form is the modular discriminant delta of tau, which is equal to q multiply everything from n equals 1 to infinity of 1 minus q raised by n raised by 24. So its Fourier expansion begins. We have delta of tau equals q minus 24q squared plus 25q 252q cubed minus 147 to q raised by 4 plus all that. The coefficients then contain deep arithmetic information. So, so if you import numbers and pick q is 0.05, n is 100. So that's like 100 times, I think. So delta is equal to q. So for n in range 1 to n, so you have your delta of t, which is one, you now have 1 minus q raised by n raised by 24. This exact expression you have here. So the product of all of that, right? So that's delta star. Star equals means that you have a recurring multiplication thing going on there, and that is how to interpret this particular expression. So if you print delta, then you have, so you start with the delta, which is q. So q multiplied by equals the next thing, and you keep going until you get to n. And here we have that to be 0.0137048629837817749. And then we see the connection between elliptic curves and modular forms. So one of the deepest theorems of modern mathematics states that every elliptic curve over the rational numbers corresponds to a modular form. Symbolically, we say elliptic curves imply modular form and modular form implies elliptic curve. This result is known as the modularity theorem. So elliptic curves, the fact that every elliptic curve over the rational numbers corresponds to a modular form. So elliptic curves correspond to modular form corresponds to elliptic curve. Then we have the Fermat last theorem. So the modularity theorem played a crucial role in the proof of Fermat's last theorem. And Fermat last theorem has something to do with Pythagoras theorem in a way. So the theorem states that x raised by n plus y raised by n is equal to z raised by n. So, and it has both trivial integer solutions for n greater than 2. So if you have n is 2, right, that's perfectly Pythagoras theorem. So the proof ultimately relied on the connection between elliptic curves and modular forms. So in summary, we have this that we talk about elliptic integrals. So study integrals such as integral of dx over square root of 1 minus x squared to 1 minus k squared x squared. And you have main object like f of phi comma k, E of phi comma k, and uh, I don't know what I think I want to call this. Should I call this pi? So it's more like some big, kind of big pi of n semicolon phi comma k. That's elliptic integral. That's where things start from, and then we move on to elliptic functions, where inverse functions of elliptic integrals have examples like Sn of u comma k. So when k is 0, it becomes sine. Then you have Cn of u comma k. When k is 0, this becomes cos u, right? Then Dn of u comma k. When k is 0, that becomes 1, and then you have the special p of z, like that. And that leads us to theta function. So infinite series associated with lattices now. Theta of z comma tau is equal to summation from n equals minus infinity to infinity, e raised power pi I n squared tau, e raised power 2 pi I n z. Then we have modular forms. So talking about modular forms now, functions satisfying f of a tau plus b over c tau plus d equals c tau plus d raised power k f of tau. So examples now, you have the Eisenstein series, you have delta function, and applications now. You have number theory, you have applications in number theory, elliptic curves, Fermat's last theorem, string theory, and of course cryptography. Talking about modular forms. And then that takes us to the practice problems. And as usual, I get to solve two of these problems before it's all over. So we see that now. Um, so I'll be solving questions 8 and 20 here. So show that the elliptic integral, this cannot be expressed in elementary functions. Compute the first three. So let me just flash the questions actually. So here we can see questions 1 to 4 like this. Then 5, questions 5 to, okay, 8 is not quite clear. So let's just leave it as question 5 to 7. Question 5 to 7, all this. Then let's go to 8 now. 8 is a bit lengthy. So now we have questions 8 to 10. Yeah, we have questions 8 to 10. So I'll be solving question 8. So show that f of z plus omega 1 equals f of z, and f of z plus omega 2 equals f of z. Then f of z plus omega 1 plus n omega 2, f of z plus m omega 1 plus n omega 2 is equal to f of z for all integers mn. So we'll be taking care of that. Then here you have 11 to 13, questions 11 to 13 here. Okay, then 14. So here you have 14 to 16, questions 14 to 16, and then 17. Okay, we can see 17 to 19 for now. And finally, 20 can show. So I'll be taking care of 20 to show that the elliptic curve y squared equals 4x cubed minus 4x is non-singular by checking that the polynomial 4x cubed minus 4x has distinct roots. So let's take care of these two problems, and we'll call it a date with this now. Okay, so I start with this problem 8. So for problem 8, the question is to show that if f of z plus omega 1 is equal to f of z, and f of z plus omega 2 is equal to f of z, then f of z plus m omega 1 plus n omega 2 is equal to f of z for all integers, m comma n. So that's what we are expected to do. Okay, so I'll just go on and start talking about the solution. So for the solution now, uh, since f of z plus omega 1 is equal to f of z, we may we may repeatedly apply the period properly, the period properly, oh, the period property actually, may repeatedly apply the period property. So that means that for a positive for a positive integer m, for a positive integer m, we can say that f of z plus m omega 1 is equal to f of z plus m minus 1 omega 1 plus omega 1. Because technically, if we expand this, that's m omega 1 minus omega 1 plus omega 1. So omega 1 cancels omega 1. So it's as good as we are still saying the same thing. And this one now is the same thing as f of, so this is as good as f of, yeah, and this is as good as f of z plus m minus 1, m minus 1 omega 1, like this. So repeating this process, so if you keep repeating that, repeating this process m times gives, repeat this m times, it will give us the fact that f of z plus m omega 1 is equal to f of z. So as you can see here, right, from this we have this, and then it all reduces to omega 1 disappearing, and then if that keeps going, we end up with just z, f of z, like this. So similarly, f of z plus n omega 2 is equal to f of z, like we already know, for every positive integer n, every positive integer n. So negative, for negative integers, right, for negative integers, right, f of z equals f of z minus omega 1 plus omega 1, and that ends up being f of, just like the kind of thing we did before. So that's f of z minus omega 1, so that f of z minus omega 1 is equal to f of z. So repeating yields, f of z plus m omega 1, f of z so that is f of z plus m omega 1 equals f of z for all integers m, for all integers m. Likewise, f of z plus n omega 2 is equal to f of z, like that, for all integers, n. Now we consider f of z plus m omega 1 plus n omega 2 so applying periodicity with respect to omega 2, we have f of z plus m omega 1 plus n omega 2 is equal to f of z plus m omega 1. So if you apply periodicity, that's what we get. So applying periodicity to omega 2, So similarly, applying periodicity, applying periodicity to omega 1, we have f of z plus m omega 1 equals f of z. Therefore, we see that f of z plus m omega 1 plus n omega 2 is equal to f of z. So this proves that every lattice translation leaves the function unchanged. The function unchanged. In essence, we're saying that f of z plus m omega 1 plus n omega 2 is equal to f of z. And that's what we are told to prove. So we go on to problem 20. Problem 20, which requires us to show that the elliptic curve y squared equals 4x cubed minus 4x is non-singular by checking that the polynomial 4x cubed minus 4x has distinct roots. That polynomial has distinct roots. So this is a question again. Show that the elliptic curve y squared equals 4x cubed minus 4x is non-singular by checking that the polynomial 4x cubed minus 4x, this same polynomial here, all right, has distinct roots. So let's go for that now. So if we let p of x be equal to 4x cubed minus 4x, and we factor p of x equals 4x into x squared minus 1. I mean, easy to factor that, right? Therefore, p of x is equal to 4x into x minus 1, x plus 1. That's why we factor this further. So we have 4x into x minus 1, x plus 1. The roots are, so when we equate this to 0, right, the roots are simply x equals 0 for this, x equals 1 for this, and x equals minus 1, x equals minus 1 for this, like that. So, and we see that all three roots are distinct. All three roots are distinct. So with that in place, then we can then go ahead to say that a cubic curve y squared equals p of x. P of x being this expression now. So a cubic curve y squared equals p of x is non-singular. It's non-singular if the polynomial has no repeated roots. And there are no repeated roots actually. So if it has no repeated roots, then it means it is singular. Okay? To verify this, To verify this, to verify, to verify this, compute, we can compute P prime of X. Of course, P of X is 4x cubed minus 4x. So P prime of X is simply 12x squared minus 4. So if we see that P prime of X is equal to 4 into 3x, 4 into 3x squared minus 1. So the roots of P prime of X would now have to be, when we equate this to 0, right? So we just have 3x squared minus 1 equals 0. So that means that we have x to be equal to plus or minus 1 over root 3. And if we equate this to 0, so we have x is plus or minus 1 over root 3. So, and we see that none of this, no, these are two solutions. They're plus 1 over root 3 or minus 1 over 3. 1 over root 3. None of this coincide. None of this coincide with None of this coincide with x equals 0, x equals 1, and x equals minus 1 that we got before. So what do we decide then? We say hence P of x and P prime of x have no common roots. They have no common roots. Therefore, the cubic polynomial, the cubic polynomial has no repeated roots. Has no repeated roots. Consequently, the curve y squared equals 4x cubed minus 4x is non-singular. 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 Thus, it is a valid elliptic, the valid elliptic curve. So we see that y squared equals 4x cubed minus 4x is non-singular. That is what we're expected to show from the question, right? uh, show that the elliptic curve is non-singular by checking that its polynomial has distinct roots. So has distinct roots, even derivatives has no answer, has no roots coinciding with the original thing. And with this, we come to the very end of this 20th video on special functions. So I'm going to flash the questions and then call it a date. So again, let's go back to the beginning. Talking about the practice problems, you can see 1 to 3 clearly here. Then you have 4 to 7 all showing here. Then I did 8 already. I did 8 over there. Then you can see 8, 9, 10 in this frame. Then 11 to 13, you can see all of that, 11 to 13. Then you have 14 to 16, all showing here, 14, 15, 16. Then 17 to 19. You can see all of 17 to 19. Then 20 now. Let me know how helpful this is for you. And if there's something else you'd like me to try out, please feel free to let me know. If you have subscribed to this channel already, I thank you very much for doing that. If you haven't subscribed, why not take your chance right now, subscribe and hit the notification bell so you can always get alerted each time a new video is released. Having done that, you can also become a member of this channel by clicking on join. That gives you some special privileges that you're going to find out when you click. Ultimately, don't forget to comment, like, and share so that more people can have access to the great content I have going on here. Till I come your way again, keep doing maths right. Bye.